Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on August 18, 2025, about 6 days ago. The Big Hook is a unified generator that creates first-person video and the matching full-body motion in lockstep, so the camera behaves like a true head-mounted view, and the actions and observations drive each other coherently. The paper is titled, EgoTwin, Dreaming Body and View in First Person, and as we will see later, the implications for embodied AI are quite significant. In short, the model uses a diffusion-transformer with head-centric motion, causal attention, and asynchronous diffusion to achieve viewpoint consistent, causally coherent results. Building on that, the tweets highlight an egocentric world model that jointly generates first-person video and matching human motion, emphasizing coherent head-aligned camera movement. One post calls out solving the dizzy camera problem with clever math. Engagement looks moderate, with just over 100 likes on the demo clip. Alright, this figure shows the end-to-end setup, inputs on the left, generated results in the center, and a 3D lift on the right. We are looking at an initial egocentric frame, a starting body pose, and a short text instruction that feed the model. The central column stacks several first-person frames with overlaid skeletons, which demonstrate viewpoint alignment because head motion drives the camera. Moving right, the large panel visualizes a reconstructed 3D scene with the generated pose sequence, showing how camera poses enable scene lifting. Next, you can see the architecture sketch that ties everything together, with encoders at the bottom, stacked transformer blocks in the middle, and decoders at the top. The left panel shows parallel text, video, and motion branches, where the motion branch uses only the lower half of layers, so it stays lightweight while still synchronizing with the others. The right panel details the shared attention core, which mixes text, video, and motion through joint attention and aligned projections. Building on the architecture, this figure illustrates the interaction mechanism that governs which tokens may attend to which others. We are looking at a grid where colored squares indicate preserved attention and empty squares indicate blocked attention, so only causal links remain. You can see the blue band for motion tokens and the green band for video tokens, with text tokens in yellow along the top. The pattern encodes forward and inverse dynamics. Video at time I attends to prior actions, while motion at time I attends to current and next observations. Now we are looking at the plot of head pose regression errors, which tests whether a simple model can recover head motion from the standard root-centric representation. The blue line shows translation error, and the red line shows rotation error. Both curves drop sharply at the first few epochs, then flatten at relatively high levels, which indicates persistent inaccuracies. This plateau supports the argument that buried head cues hinder alignment with first-person video, so a head-centric representation becomes necessary. Now we are looking at the main results table, which compares vid-MLD against EgoTwin across video quality, motion quality, and cross-modal consistency. You can see lower is better for image frame distance, frame video distance, motion frame distance, and the translation and rotation errors, while higher is better for clip similarity, retrieval precision, and hand score. EgoTwin wins across every column, which signals better visuals, stronger motion, and tighter head-aligned viewpoint behavior. Alright, this figure presents qualitative joint generations, a row of first-person frames on top, with two boxed condition frames at the ends, and a synchronized sequence of blue skeleton poses underneath. We are looking at smooth viewpoint changes that match turning and walking, which shows head-aligned camera motion tracking the pose. You can see the skeletons lean and rotate when the hallway view bends, so visual dynamics and actions progress in lockstep. Now we are looking at the ablation table, which isolates 3 design choices and reports video quality, motion quality, and cross-modal consistency. You can see rows for without motion reformulation, without interaction mechanism, and without asynchronous diffusion, followed by the full model. The full model achieves the lowest image frame and frame video distances and the lowest translation and rotation errors, so viewpoint alignment improves. The full model also delivers the highest clip similarity, retrieval precision, and hand score, which signals tighter video-to-motion coupling. Continuing from those ablations, 2 takeaways stand out. The head-centric motion reformulation is the linchpin for viewpoint alignment, and the cybernetics-inspired attention mask, which restricts who can attend to whom in time, delivers causal video-to-motion coupling. Diffusion-transformer here just means a transformer that learns denoising steps. Thanks for listening. This is Alex, signing off from AI Research Roundup.